Okay, guys. So today I want to continue a discussion about integration. So just want to remind you that last time we talked about the indefinite integral, and there was one last example that we did just to show you that computing integrals is not as straightforward as just using the basic definitions. And then we did this last example, the integral of x squared times the square root of x cubed minus 1. And then the way that we actually solved this was by using a technique called integration by substitution. And then I just wanted to show you a complete example of that. Okay, so now let's go ahead, take a step back, and understand why is it that we can do something like this, and then to streamline this process, and we're gonna do more examples. Okay, so this is the main goal that I have for today, because I want to make sure that you get this technique of computing indefinite integrals down. This is going to be very important for you in the following course as well. And then what I'm going to do is I'm going to ask you to read. So at the end, I'm going to tell you what to read and what to watch. But I'm going to ask you to read and watch videos regarding the definite integral and the computation of area. Okay, so that on Monday, when we come back, next class, I will actually summarize the information so that we can have time to do examples. Okay, otherwise the whole class time is going to be myself explaining the development of the theory, and then we're not going to have time to do many examples, and I would like to do several problems because it will be our last lecture. Okay, so this weekend you will be doing some reading regarding uh, the computation of area so that you will be prepared for Monday. Okay, all right. But anyways, let's get back here and let's talk about solving this technique called integration by substitution. So I guess say here this is called integration by substitution. This is what we did last time. Okay, the last example that we did last time. Then let's streamline this process now. Okay, so integration by substitution. So remember, as I mentioned before, and now that we are talking about this notion of integration, there is a very close relationship between integration and differentiation. So in particular, almost every rule that we have on the derivative side will in some way translate as a rule or theorem on the integral side. Okay, and in particular on the differentiation side for the derivative, we have a very important rule called the chain rule. So let me remind you this. All right, so called the chain rule. So remember, what does the chain rule says? So suppose that we have a function, let y be a function of some variable u, and then u is a function of x. Okay, so then that means that you can think of y as a function of x itself by just replacing u by g. So you look at the composition, right? So if you have a composition of two functions, like in this case, I'm using capital F purposely for a reason, okay? Then what the chain rule says is that if you take the derivative with respect, you can take the derivative with respect of x of this composition. So if you take the derivative with respect of x, then what is this equal to? This is going to be equal to the derivative of the outside function evaluated at the inside times the derivative of the inside function, right? That's what the chain rule says. Okay, so now again, every almost every rule on the derivative side will give you something on the integral side. Therefore, this chain rule that we have for derivatives, which has to do with composition functions, how you take the derivative, will translate into some statement or technique on the integral side, and that's the so-called integrations by substitution. So let's explain this. So for example, we have this, because we have this derivative, then what does this mean on the integral side? Okay, let's do the following. Remember that we said last time that integration and differentiation, they kind of cancel each other. quotation mark. Remember, they are not exactly inverse, but in general, you can think of them that way. So let's look at the derivative of the composition. Let me do it in this. Let's look at the composition of the function, take its derivative, and then let's take its integral. Okay, so before I do anything, we know exactly what's gonna happen. So what will be the final outcome of doing this? So remember, when you do it this way, what happens? You take the derivative of the function, and then the integral comes in, it counts as the derivative, so you're gonna get back the original function that you started with. But remember, because the last thing that we're doing is the integral, it's not exactly the same function, you may come back with an additional constant being added to it. Okay, there's this plus c. So, they are inverse of each other up to a constant. Because when you do this derivative first and then integral, you don't have to get exactly the same function. But you get a version of it. Okay, so we know that this is going to happen. Okay, if we start with this operation on the left, we're going to end up with this result on the right. Now, let's take a look at what happens in the middle. That would be the interesting thing. So in the middle, what is it that we get? Well, we have the integral of, so let's take the derivative because that's a composition. That's going to be f prime of g times g prime. That's using chain rule. Okay. So now, if we ignore the left-hand side, the first term on the left, then we focus here, we get a statement. Okay. And that statement is telling us that whenever you have a shape like the one that you're seeing here inside the integral, like something that looks like the blue integral, we can actually compute it by just figuring out what this capital F is and then evaluating that at G, and then that's it, you're done. Okay, so this is the heart of what we call the integration by substitution. So let me streamline this idea. This is what we call the substitution method, and it comes from what we just observed here, that it comes directly from the chain rule. Okay, all right, let me write it down. So suppose that you have a continuous function. So let f be a continuous function on an interval I. And suppose that g is a function whose range is contained in this interval. In other words, the range of g is part of the domain of f. Okay. So if the function g is differentiable on its domain and capital F is an antiderivative of little f. So remember, basically what I'm saying here is that if I do f prime of capital F, I get little f. That's the notion of antiderivative. Okay. On this interval I, so that will be for all x in I, that equality that I just wrote holds. Okay. Then, so now let's see, what statement do we obtain from here? Notice that in this case, little f is playing the role of capital F prime. So if you look at the box that we have above, you could rewrite this as little f of g of x. Okay, so that's what I'm gonna write in the theorem. Okay, and then capital F is just an antiderivative of little f. Okay, so then the statement is that the integral of f of g of x times g prime of x dx. So if you come across an integral like this, or if you can change your integral to look like this somehow, then to evaluate it, all you have to do is figure out what is an antiderivative for the function f. We know what it is, capital F, and evaluate it at the function g. Okay. Now you may wonder yourself, well, what do you mean by substitution? What is the substitution happening here? Well, let's uh, let's relabel some of the terms in this expression that we just obtained. Again, this is just straight from the chain rule. Let's relabel some of these expressions and then let's see what we obtain. as we started above, remember this g is the inside function in the composition. So we can call this function, let's call it u, okay? As you see above for the chain rule, the same thing here. So I'm gonna take this guy, I'm gonna call it u, okay? So let u be equal g of x, okay? Then remember, this means that I can take the derivative of u. So then du dx is just g prime. And as I mentioned before, that means that we can say then that du is going to be equal to g prime of x dx. Okay? All right. So in other words, just take this guy and move it over here. Okay? Okay. So du is g prime dx. So now let's go ahead and let's make a substitution. So then the expression, the integral expression that we have above, what does it look like? Then we're going to obtain the integral of f of u, because g now is equal to u. Now the part that says g prime of x dx, that's just du, as we just figured out. Okay? And then notice how the integral, just by looking at it, it looks simpler, right? So the first integral, it looks a little bit more complicated, but after we make the substitution, now we obtain something simpler, because we already have an antiderivative for little f. Then the result here is just that antiderivative, but this time evaluated at the function u. And then of course plus c. Okay? And then, once you go through this process, then at the end, remember, this substitution is just a technique that you use to make your integral simpler. You solve it, but then you have to put back whatever u was equal to, which in this case is the function g. Okay? And this is where you see the substitution taking place. So now, if you look back at the example that we did last time, you will notice why we make such a substitution. Because remember, basically what you want to do is you want to see if you spot a composition in the expression that you're trying to find the integral of, and then hopefully you realize that the composition is happening right here, right? So here you can think of this as being f of g of x, for which f is the outside function, right? Square root, and g is the inside function, x cubed minus 1. Okay? And the moment that you realize this, then the next question is, okay, I also need g prime to show up in the integral. Well, you know that g prime is 3x squared. We technically don't have 3x squared, but we have 3 squared. We have an x squared. So you can think of this as being g prime over 3, right? If you divide g prime by 3, that gives you x squared. You can get it from here, right? G prime over 3 equals x squared. And therefore, that means that we can make the substitution work. As you can see in the example, our substitution is working nicely. Indeed, we got a simpler integral, this one here, and something that we know how to solve. We solve it, and then at the end, once we get a result, we put the original variable back. Okay? All right. So let's do some examples just to get used to this idea. So again, the secret is you may want to think about substitution. I'm saying may because there are situations in which that's not exactly this form has to follow, but the substitution will still work. Okay, you will see examples of that. But basically, the idea is, because the main question always is, okay, what should be my substitution to make my integral work? Okay, here is more or less a clue. You have to look at your integral. See if you spot a term that looks like a composition. Okay. Once you spot that composition, your g, your u, the substitution that you make will be your g, which should be the inside function. Now, don't just blindly pick the inside function. You have to make sure that you have the other term showing up outside, which in this case is a g prime. Okay. So you want to make sure that when you pick your u, you have a g prime that you can figure out. Okay, that's multiplying the composition that you have outside. If you don't have such a g prime, then the substitution that you want to make, that is not gonna work. Okay. Now remember what I told you last time. If your g prime, if the term that you have outside is off by a factor, by a constant, by a factor of a constant, that's okay. You can always fix that because you can move constant around by dividing and so on. Okay. But if you're off by a variable, then that's not good. Okay, by a power of a variable, maybe you needed an x squared and you only have x. Well, that's not good. Okay, but if you have an extra power, you only needed x, but you have an x squared. Again, that's not good. So there you need to try something else. But if you're off by a constant, that's not really a problem. Okay, so anyways, let's go ahead and let's do some example. As I mentioned last time, the only way to get a hang of this is sitting down and do problems. Okay, so just practice, 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 so that when you look at a problem, you can immediately say, okay, this is my substitution. I'm gonna do it. I know it's gonna work. Okay. All right. So let's do some examples to illustrate this technique. So examples, and I'm gonna do some basic ones, and then we're gonna do more interesting ones. Okay. So find the antiderivative. So find the antiderivatives. And let's see, I'm gonna write. So we did one last time. Now let's do this one. This one is gonna be, it's very obvious. But it's just to illustrate the idea. So let's say that we have something like this. By the way, you could do this problem by, if you want, by taking the long way. Okay. What would be the long way? The long way would be by expanding the square. You have square plus 1 square, right? So you expand that term, you're going to get a degree 4. Then you distribute the 2x, you're going to get a polynomial of degree 5 in this case. And then you integrate the polynomial by using power rules. There's nothing wrong with that. The problem with that method is that if instead of having a 2, what if I had here a 2022? Okay. If I have something like this, you're not gonna distribute this 2022. You're not gonna do this binomial and then distribute it to x so that then you can integrate. So, I mean, sometimes that may be your only choice, but in this case, we can use cleverly substitution to address this problem. Okay, so we can do it by using substitution. So I'm gonna keep it down to 2, but I want you to understand that the power here is really irrelevant for the technique that I'm about to show you. Okay, let me just keep the square here. Okay, anyways, so I want to use this, I want to do this problem by substitution. So again, we need to spot this and try to see, look at the problem and try to see if you find a composition. Okay, and then hopefully you realize that right here we have a composition happening, right? In which my f is the x square function and g is x squared plus 1. This is the inside function. Okay. All right. So that's a good sign. We see a composition. Then the next thing is, okay, what do we need to have outside? Look at the formula. We need to have a g prime. So do we have a g prime? Well, yes. If that's my g, then notice that we exactly have g prime here outside. So this nicely fits the pattern of the formula we have above. So this is, according to the theorem, is supposed to be capital F of g of x, where capital F is an antiderivative of little f. Well, let's go here. If little f is x squared, what is capital F? As you know, we just do a little power rule. So that would be just the integral of x squared. So that's x cubed over 3. Okay, that would be x cubed over 3. And yes, it is plus c, but let's call it c1. This plus c, when we put it on our final result, combines with the other c, giving you once again an arbitrary constant. Okay, So typically here we're just finding for an antiderivative. So you, I'm just gonna erase that because I don't want all of them. Remember that integral notation represents all antiderivative. I only want one antiderivative, which in this case is just x cubed over 3. So that means that then this is gonna be equal to plugging g into this function. So we're gonna have 1 over 3 times squared plus 1 cubed. So I'm just plugging in x squared plus 1, which is g, into my antiderivative. Okay? So again, we did this without, I didn't really use substitution. We just recognize the pattern showing up and then we're able to solve the problem. Now let me do it using substitution because sometimes the pattern doesn't really show up, but the substitution allows you to change the integral so that then you get something easier to solve. So using substitution, and then from now on to practice this, I'm going to be using substitution instead of trying to spot for the pattern. But if you see the pattern, just use it because then it's quick, okay? All right, so if we want to use substitution just to streamline the process, for example, instead of doing a square, let me now do the 2022 version, okay? But again, it's exactly the same thing. Same problem. The technique is exactly the same. The only difference is that instead of a square, we have a 2022. It's a power. Okay, so I look at it, I see my composition, so I know that if I'm gonna make a substitution, I should make it be the g, the inside function, and just visually inspect. Can I find it? Is the derivative of this function of this substitution in the expression? Yes, because the derivative of x squared plus 1 is 2x, and I see it there. So we're good to go. So I'm gonna let u be equal to x squared plus 1, okay? So that means then that du, remember du just stands for derivative. It's differential, but you can think of it as just taking the derivative. So then the derivative is 2x, but then we put a dx in here. Remember that dx was here, but then we move it over here, okay? So if u is equal to x squared plus 1, then du is 2x dx. So we have everything we need, right? So now when you do the substitution, just look at the integral. What we're doing is we're changing everything that was in terms of x, now we want to write in terms of the new variable u, okay? So the first factor, we can write it as u to the 2022, okay? And then the second expression that we have, which is 2x dx, we can write it as du because 2x dx is du, okay? According to our substitution. Now notice that when you look at it from this point of view, all we did was change. We had a problem that may look a little bit complicated, right? But then we just, by making this little substitution, we change it into something that is way simpler that we can actually solve. Now here we do the usual power rule. So this will be 2023 or 2023 plus c. And remember, put back whatever u is equal to. So that would be 1 over 2023 times x squared plus 1 to the 2023. Okay? All right. So let's see. Let's do another one. How about the integral of e to the 5x dx? Let's do this one. Okay. So for example, here I guess you can probably guess what the result is going to be by just finding an antiderivative. But let's say that we want to streamline this process, right? For example, when you see this expression, you know how to find the derivative of e to the x, right? Now, what should be the derivative of e to the 5x? You can just reason through it and say, well, I know that if I take the derivative of e to the 5x, I'm going to get 5 times e to the 5x. So if you divide by 5, then you're going to get e to the 5x. So, we are expecting that the result here should be this, okay? just to compensate by the chain rule. To compensate that times 5 that you obtain, you divide by 5 to cancel it when you take derivative. And that's going to give you e to the 5x when you take the derivative. Remember, because to check, what you do is take derivative of this, and it has to give you this. Okay? Now, instead of using that reasoning, which is what you should do to quickly do a problem like this, let's keep practicing substitution. For example, okay, you should realize that there is a composition happening here. Basically, here is my inside function, right? My outside function is e to the x, and the g, the inside function, is 5x. So I'm gonna make my substitution. I'm gonna let u be equal to 5x. So then that means that du is gonna be equal to 5 times dx. So I don't see 5 anywhere, but that's okay. I have a dx. Remember, if you're off by a constant, by a factor of a constant, that's not a problem. Because remember, this just means that dx, you can rewrite it as du over 5. The idea is that anything that's in terms of x, you just want to do something that's valid, of course, algebraically, and to write in terms of u. This is what you need to have in mind, so that then you can make your substitution. But let's see, here we are ready then. So the first term, e to the 5x, we can then rewrite it as e to the u, and then dx, we can rewrite it as du over 5. And now let's integrate this. So notice that this over 5 is just a constant, so I'm going to put it outside. So we have the integral of e to the u du, and as you know, e to the u, that's just e to the u plus c, and now we put back what u is equal to, which is 5x. So yeah, 1 over 5 e to the 5x plus c, as predicted earlier. Okay, all right, so let's see, let me do a similar one. For example, we can use a similar idea. Let's say that you wanted to figure out the integral of cosine of 2x dx. What is this equal to? Well, again, I know how to integrate cosine, but how do we integrate cosine of 2x? Well, here is what we can do. Once again, we see a substitute, we see a composition here, and the inside function is a 2x, so just visually do it. So if I let u equals 2x, I know this becomes cosine of u, which is something that I can do when I integrate. The question is, do I have everything I need to make the substitution? Well, if u is 2x, I need to have a du. So du will be the derivative, right? So the derivative of 2x is 2. I don't see a 2, but that's fine because it's just a constant. When you're off by a constant, you can always fix it by doing the trick that we did above. You just, rearrange, divide, and so on. So we can make it work. We let u equals to x. So du is 2 dx. And as you know, this means that dx can be written as du divided by 2. So this becomes cosine of u times du over 2, which is 1/2 the integral of cosine. And as you know, the integral of cosine is sine. So this is going to be 1/2 sine of u plus c, which is sine of 2x over 2. Okay? So basically the idea is, okay, you know the derivative of sine is cosine. So you have cosine of 2x. You know that if you look at sine of 2x, its derivative, what is it going to be? It's going to be cosine of 2x, but then times 2 because of that chain rule. So to compensate, to get rid of that times 2, that's why we divide by 2. As the mindset that you may want to have if you wanted to do it directly instead of relying on the substitution. But the substitution is nice because, even though it may seem like a bunch of little steps, it streamlines this process and, of course, allows you to deal with more complicated situations. Okay? So, let me do another one that comes up very straightforward as well. So let's do secant squared times tangent of x plus 3. So you have something like this. It's not necessarily a composition that we have here, but however, you can see here that there is an expression so that, for this substitution to work, all you really need is that whatever you decide u to be, its derivative or a version of it has to show up in the expression as well. So you can find your du, okay? That's basically the idea. So even though, you don't see an actual composition taking place here, I mean, we do have secant square, but that's not really gonna help us much. Uh, but in this case, I see a tangent. And in fact, I see the term tangent plus 3. Why am I incorporating the 3? Well, because the derivative of tangent and derivative of tangent plus 3 is the same. Okay? And the bigger your u is, the better, because the simpler the integral will become. Anyways, by looking at this, if I call this guy u, notice that then the derivative of u is exactly this one. Okay? So then this will be my du, because the derivative of tangent is secant squared. Okay? So I'm going to let u be tangent of x plus 3. So that means that du is going to be secant squared dx. So this integral becomes the integral of u du. Because again, the parenthesis is just the variable u, and then the secant squared dx becomes du. Now you know that this is u squared over 2 plus c, and then we put back what u is equal to, which is tangent of x plus 3. So this is 1/2 times tangent plus 3 squared. Okay. All right. So we have done some simple, some somewhat straightforward examples. Let us now look at more interesting ones. Okay. So let's put here more examples. Here I want to put a bunch of integrals, and then let's solve them. So solve the integrals. And then let's see. So let's do the integral of x cubed over the square root of 1 plus x to the 4. Okay, I'm gonna write them all here. If you want, just pause this and try to do them yourself first. And then, hit play and keep looking and see how I do it. But I'm gonna, challenge yourself. Try to do it first on your own. Okay, so this one, then let's see, we talked about differential equation last time, so let me ask the question now in the differential equation language. So solve the equation y prime equals x squared times square root of 1 minus x. So remember, this is just a fancy way of asking you to compute the integral of the expression that's on the right, because solution will be all antiderivative of the expression on the right. So to do number 2, you have to compute that integral. Okay, number 3, for example, let's do tangent. I mean, we have a formula for a bunch of the trigonometric functions, the simple formulas, but the basic formulas. But we don't have a formula for tangent. What's the integral of tangent? What's an antiderivative of tangent? All right, let's figure it out. Um, let's do, okay, so let's do the square root of 2x minus 1. Okay, so that one is fine. So let's do e to the tangent of 2x times secant square of 2x. Okay, just want to do several examples here. Let me actually So use, okay, that is fine. And then number 7, let's put some more interesting ones here. E to the x over the square root of 1 minus e to the 2x. And then let's do e to the square root of x over the square root of x. Okay, so here we have 8 problems. So as I said, just challenge yourself a little bit. Go ahead, just, hit pause and try these problems on your own. See if you can do them, okay? Or at least try a couple, right? Try number 1, then, watch the solution, then pause, then try number 2, and then, if, after you think about it a little bit, if you do it, then watch the solution to make sure that you did it correctly and so on. But try these problems first so that you start thinking about these and see if you can figure out some technique or some way of dealing with this. Like what substitution should you make? What manipulation do you need to do to manage to find an antiderivative? And then, of course, watch to see how we do it. But if you just passively watch the video, you're not gonna gain much of an understanding versus if you actually sit down and try to do these problems first. I mean, you already have the idea and the theory to do it. Now it's just a matter of sitting down and problem solving. Like think about how you can solve the problem with the knowledge that you currently have. Okay, so hopefully you follow my advice. You pause, just you work on the problems. Now let's come back and let's do these problems one by one. Okay. All right. So the solution. Let's see. Number 1. We have the integral of x cubed over the square root of 1 plus x to the 4 dx. So first of all, every time that you see an integral, try to see, if you can compute it immediately in one shot. If you can't, then that's when you start thinking about other techniques. All right, so here looking at this is, there is no splitting, nothing easy that I could do that allows me to solve this integral nicely. So I'm gonna see if I can try to do some substitution to make the integral nice. So then I look at my expression and then I wonder, okay, what substitution should I make? So you need to look for something whose derivative is also there. And also remember, clues for this is places where you spot a composition. I see a composition taking place in the denominator, the square root with a 1 plus x to the 4. And if you look at this, the derivative of x to the 4 is 4x cubed. I don't see a 4, but I see an x cubed in the top next to the dx. That's good enough for me. Okay? So we're going to let u be 1 plus x to the 4. Then that means that du is going to be 4x cubed dx. And I see an x cubed dx in the top. So that means that if I divide by 4, I can replace x cubed dx by du over 4. So let's make a substitution then. So this then becomes the integral of 1 over the square root of u. And then the x cubed dx, I can write it as du over 4. Okay, now the question is, do I know how to solve the integral that we just obtained? Because all we did was change the first integral for the second integral, and this only is meaningful to us as long as we get something that we can solve. Well, at least this one looks simpler, and moreover, yes, we can solve it because this is just power rule. We can bring the 1 over 4 out, and the square root in the bottom, we can rewrite it as u to a negative 1/2. And now we are in business. We use our power rule. So we get 1 over 4, and then u to the negative 1/2 plus 1. Let me remind you of that. Okay. Remember, you add 1 and then divide by that. So that would be 1 over 4 u to the half over 1/2. So these 2, it goes really to the top. So it's going to cancel with the 4, giving me a 1/2. So the answer is going to be 1/2 times square root of u. Well, so that's the simplification. And then remember, don't stop here. You don't want to give the answer in terms of u. You need to give the answer in terms of the original variable, which is x. So what was u equal to? 1 plus x to the 4. So that's what we write. So we get 1/2 times the square root of 1 plus x to the 4 plus c. Okay? All right. So that was number 1. Let's let's do number 2. Okay. So number 2 is we have the differential equation y prime, which is x squared times square root of 1 minus x. Okay? Well, remember, to solve this is to figure out what is y. Well, we have y prime, but y will be an antiderivative of this, right? A function whose derivative is x squared times the square root of 1 minus x. So our function y is just the integral, or the family of all functions that satisfy this is represented by this integral. So to solve this differential equation, all we have to do is integrate. So that's what I'm about to do. Okay, so we're gonna find the general solution. Now, here, this is an example in which, what we have been doing before doesn't really accommodate with what's have been happening. And what do I mean by that? Remember, so before we have been looking for a function, so when you make your substitution, the derivative is in there for a g, okay? Now here, it's not really that I wanna have the derivative in there. Of course, you always, for the substitution to work, you have to make sure that the derivative is outside so you can find your du. But here, the purpose is not to actually make the integral smaller, quotation mark, or simpler. It's just to change the form of the integral so that I can actually solve the form that I obtain. What do I mean? Well, let's look at this integral. What do we do here? The moment that we see this x squared times and square root of something, we already stuck because there is no way to distribute this. Now, if the role of this, if the position of the square root and the squares were in a different place, like for example, if instead of x squared we had on the x, we had the square on the 1 minus x, and the square root we had it on the x. In other words, if instead we had something like this, just switch the role of the square root and the square, then I know how to solve this problem because we can expand this square, right? Get a trinomial, then distribute the square root, and then you use power rule. Okay? So the trick that I'm about to do, I'm gonna take advantage of substitution to make something like this happen, to switch the role of the square and the square root. Okay? So keep in mind that substitution also allows you, to manipulate the shape of your integral so that you can get something that hopefully you can solve. Okay? All right. So what I'm about to do is to motivate that. So instead of having the square root of 1 minus something, I want to have the square root of something, just one term. That's the reason why I'm going to call all of these u, okay? Because then when I make my substitution, I'm going to have a square root of u. So let u be equal 1 minus x. Now, this will only work as long as I can find my du, okay? Now, luckily, if I do that, that just means that du is minus dx, right? And again, I have my dx. All I need to do now is put a -1 just to compensate. But that's it, okay? And that's not really a problem. So dx is negative du. So far so good. So let me do this little by little. So far, this is looking like this. Square root of u, and then the dx part becomes negative du, okay? So let me rewrite it as -1 times du. Okay, now why did I leave a space? Well, because we still need to do something about that x squared, okay? So what can we do about x squared? Well, here is the magic or beauty of the substitution. We can now manipulate our substitution. Because u was equal to 1 minus x, then what does that mean about x itself? That means that x is 1 minus u, right? Just solve for x in your substitution. So if u is equal to 1 minus x, then x is 1 minus u. So x squared becomes 1 minus u squared. So notice how we actually obtain what we wanted, right? We switched the role of the square root and the square, and we already had a plan. If we manage to do that, then we know how to do it. Expand the square, distribute the square root, power root. Then, of course, there was a price that we needed to pay. We of course don't get exactly the same integral. What was the price that we pay? There is this -1 pops up if we wanted to do that change. But that's okay. That's a very small price. So let's do it. So then I'm gonna put the negative outside, okay? And then I'm gonna have my square root here. I'm gonna write as u to the 1/2, and then the 1 minus u squared, I'm gonna expand it. That's 1 minus 2u plus u squared. Then I'm gonna have my negative here. I'm gonna distribute. So that's u to the 1/2 minus 2 u to the, so 1/2 plus 1, that's 3/2, and plus, then 1/2 plus 2, that is 5/2. Okay, now what is this? This is gonna be equal to negative. Now let me put a big parenthesis here or bracket, because what I'm about to write is going to affect the sign of everything that's inside. Okay, because of the minus. And this minus affected the sign of everything that I'm about to write. Okay, so now we have three little integrals here, and we use power rule on each of them. Okay, so the first one is u, so it's 1/2 plus 1, so that's 3/2 over 3/2, and 2 times, now 3/2 plus 1, that's 5/2 over 5/2, and then 5/2 plus 1, that's 7/2 over 7/2, and then plus c. So now I'm going to distribute, clean stuff up, and also put back the original variable. Okay, so I'm going to do several things at once now. So that would be negative 2 over 3, and remember u is 1 minus x. 1 minus x to the 3/2 plus 4 over 5, because the 5 over 2 becomes 2/5, and then times 2. 1 minus x to the 5/2 minus 2 over 7, 1 minus x to the 7/2. Okay? And this is the general solution to the differential equation above. So even though it looks big and so on, notice how the substitution actually kind of helped streamline this process. And here, just giving you the idea that, when you do substitution, you can play with your variables, you can play with expression, as long as what you do is valid algebraically, no problem. As long as you change, the goal is to change the integral into something that you can solve. That's it. Okay. All right. So that was number 2. Okay, number 3, tangent. So what's the integral of tangent? How do we do this? I mean, we don't have, at the top of our head, there is no function whose derivative, there is no basic function, so when you take the derivative, you get directly tangent, right? We know we know the derivative of tangent is secant square, but the integral of tangent is a different story. You need a function whose derivative is tangent. Well, here is what we can do. As a general rule, whenever you see tangent and if you don't know what to do, just write a sine over cosine and see where it takes you. So that's what I'm gonna do. Instead of tangent, I'm gonna write it as sine over cosine. And the moment that we see this, then hopefully you start, and if you have the practice of substitution already, you can already spot something interesting. Remember, the basic idea is, do you see something so that when you take the derivative is also there? And you could say, oh, I see sine, derivative of sine is cosine. Yeah, but be careful, you don't have a cosine here, even though you see cosine. What you have is a 1 over cosine, because when I say the derivative is also there, it has to be next to the dx. And what you have next to the dx, if you look at it from that point of view, is a 1 over cosine. and that's not good. That's a secant, really. Okay, so sine is not a good choice for a substitution. However, how about cosine? If we let u equals cosine, then du is gonna be negative sine dx. Yes, sure, I don't have a negative, but that's not a problem, as you know. And we do have a sine dx showing up next to each other. So that's your clue. So I'm gonna let u be equals to cosine, okay? Then du becomes negative sine of x dx, meaning the sine of x dx is actually negative du. So the problem becomes the integral of 1 over u times negative 1 du. And we know exactly how to solve this, right? So put the negative outside, and then that will be negative integral 1 over u du. And the integral 1 over u, remember, is ln of absolute value of u. And now we put what u is, which is cosine. So here we have the antiderivative for tangent. Now, typically, instead of leaving it like this, you can leave it like this, it's not a problem. But typically what we do is, we manipulate this a little bit more. This negative, we can bring it here. So you can write this as ln of the absolute value of cosine of x, to the negative 1. And then, as you know, cosine of x to the negative 1, that's 1 over cosine, which is secant. So, and this is, it's a little bit nicer just because it doesn't have a minus, right? So ln of absolute value is secant. If you take derivative of that, that's going to give you tangent, okay? So remember, if you take derivative, what is this? That will be 1 over secant times the derivative of the inside. Derivative of secant is secant tangent, right? Secant cancel, and then you get your tangent, okay? All right. So I'm going to box this one because I like that one better because it doesn't have the negative. Okay, so that is number 3. Let's see, number 4. Square root of 2x minus 1. Okay, so here, there's not much to do. If you don't see how to do the problem directly, there is only one substitution that you can make, right? So that is really not much to think about. The point is that if we let u equals 2x minus 1, then this becomes square root of u, and we know how to integrate that. So the question is, when we made the change to have the square root of u show up, whatever comes up, can we deal with it? And in this case, yes, because it's just a constant. So if we let u be equal to 2x minus 1, then du is 2dx. So we are off by a constant. That's not a problem, as you know. This just means that dx is du over 2. So this would be square root of u times du over 2, meaning that this is going to be a 1/2 u to the 1/2. So power rule now. So that's u to the 3/2 to the 3/2. So the 2's cancel out. So we get 1/3 times 2x minus 1 to the 3/2. So don't forget to go back to the original variable. Okay? Don't forget this. To go back to the original variable. Okay. So that was number 4. Again, just want to give you a bunch of examples so that you can remember this. Just to be good at integration, you just need to do practice. You have to sit down and do problems. It's really no other way. You have to develop an intuition, a problem solving for this. You have to look at an integral and you need to know what to do. Like when you look at number 5, you know, stare at it a little bit, and then you should realize, oh, I'm gonna let u be equal to tangent of 2x. Why? Well, because du is tangent square, and is secant square. Sorry, du is secant square, and we have a secant square there, okay, next to the dx. Yes, sure, it's secant squared times 2 because of the chain rule, but that times 2, even though we don't have it, is not a problem. You're off by a constant, you can deal with that. Okay. Same thing with the number 6. You look at number 6 and you say, well, what can I do? Well, I can let u be equal to sine of 3x. Not sine squared, sine of 3x. Why? Because there is a sine is cosine, and I see a cosine of 3x in there. And once again, you're going to be off by a constant, but you can deal with that situation. Okay? All right. And then we're going to get to 7 and 8. But which again, is a sort of similar thinking, but they have their own flavor to it. So we'll talk about it. All right. So let's see. Let's do number 5. So that was e to the tangent of 2x times secant squared. So e to the tangent of 2x and then times secant squared of 2x dx. So again, I'm gonna let u be equals to tangent. And again, the idea is because I want to make my problem simpler. I want to solve a simple integral. I don't want something big like this. So then the derivative of tangent is gonna be secant squared, but remember, times 2. Okay, and then we just stick the dx in here. And you take a look at your integral, and then you see that we have everything in there except the 2. So this 2, let's move it to the other side. So that means that secant squared of 2x dx, the substitution for that is going to be du over 2, or 1/2 du. Okay, so this becomes e to the u, and then secant squared dx is du over 2. So it's going to be 1/2 integral of e to the u is just e to the u, and then we put back u is equal to, which is tangent of 2x. Okay, so hopefully this is making sense to you. All right, so this one, number 6. So we have sine squared of 3x times cosine of 3x. Okay, all right, so this time I'm going to let u be equal to sine, just sine, not sine squared, because if you do sine squared, then the derivative of that is going to be 2 sine times the cosine and then times the 3. But I guess, yeah, no, that's not gonna work, because even though you can find the sine cosine here, then there is another sign, and then what do you do? Because if you do sine squared, that substitution is not gonna really do any good to you. So anyways, here what really will work was just letting u equal sine of 3x, because there is sine cosine. I see the cosine right there. Okay, so then this becomes cosine of 3x, but then remember, times 3. Okay, it's chain rule, derivative of the inside, so don't forget the chain rule. All right, so right here you can see then that the cosine of 3x dx is du over 3. I'm just not gonna write the extra line. Okay, just gonna do it directly. So this becomes u squared, and then cosine of 3x dx, that's just du over 3. Okay, again, this 3, just move it to the other side. Okay, dividing. Okay, so it will be 1/3, and then the integral of u squared, that's u cubed over 3. Okay, and so this becomes 1/9 sine cube of 3x. Okay, all right, so again, remember, I hope that you try to do this on your own first, so that then hopefully if you didn't, if you saw a solution, very good, and then you're confirming what you did. If you didn't see a solution, then uh, Just now, when you see the way that we are solving it, then hopefully something will click in, and then you will start gaining more of an understanding. It's better to try something on your own first, and then look how it's done, than just looking how it is done from the beginning, because you don't get so much of an understanding by doing it that way. Unfortunately, in class, I don't have enough time to let you try a bunch of problems on your own first before I start explaining the examples. Otherwise, we don't finish anything. But ideally, you should have time to think about the problems first, and then I show you how they are done. So I guess in that respect, the video works nice because you can pause, try yourself first, and then continue. Okay, anyways, let's take a look at this one. Once again, if you didn't try this, just pause the video, think about it. Try to see if you can figure out a way out of this problem. How can you solve it? Okay? All right. So, what can we do here? And so, we see an e to the x, we see an e to the 2x inside a square root, 1 minus e to the 2x. Things don't look too nice in this respect. By the way, if this was a 2x here in the top, it would be nice because we just let u equals 1 minus e to the 2x in the bottom, this guy. And then my du is going to be minus 2 e to the 2x, which is on top, the e to the 2x, so we can make it work nice. Now, the thing is that we don't have an e to the 2x, we have an e to the x in the top. But that's fine, that's not really a big deal, as you are about to see. The trick here is to realize that the e to the 2x in the bottom, we can write it as 1 minus e to the x squared. Remember, the exponent of an exponent, you multiply, right? And then the moment that I do this, then at least we can simplify this greatly, because if I let u be equal e to the x, then my du is e to the x, which is right here on top. Okay? So I'm going to make this first change, and then let's see what we obtain. If u is e to the x, then du becomes e to the x dx. So now we have the integral of 1 over square root of 1 minus u squared du. And so the question is, can we solve this integral? Well, if you think about it a little bit, you should realize that this is actually one of our basic integrals. This is the arcsine, or the inverse sine integral. So this becomes inverse sine of u, and therefore the answer here is the inverse sine of e to the x. Okay? And then finally, let's see, let me do one more. Integral of e to the square root over square root. Again, pause, try to see if you can do it. So what do we do here? Well, and we see square root here, and then the question is, if I let u equal square root, what's the derivative of square root? Well, remember, square root of x, the derivative is 1 over 2 square root. And I do see a 1 over square root, so that's good. So that means I'm going to let u be this guy. Okay? So u equals square root of x. So du is going to be 1 over 2 square root of x. And I have a 1 over x dx in there. All I need to do is move the 2 over. So let me do it. So that means that 2 times du becomes 1 over square root of x dx. So my integral becomes e to the u, and then times 2 du. Because 1 over square root of x dx is 2 du. So the answer is 2 e to the u. So that would be 2 e to the square root of x. Done. Okay. All right. So Hopefully, with all of these examples, I've done a lot of problems for you, showing you this technique of substitution. This is going to be your most valuable technique when it comes to solving integrals. And you're going to be using this all along throughout the entire calculus too. Like at least two-thirds of the course, you're going to spend it doing a bunch of integrals. And at the end of the day, they will boil down to some type of substitution most of the times. Okay? So make sure that you're comfortable with this, that you understand how to do something like this. So let me see. I mean, I'm gonna present, and we're gonna do more examples on Monday, even though we're gonna be talking about another type of integrals, the definite integrals and so on. At the end of the day, when we do problems, you're gonna see that it's gonna be very similar to what we're doing here. So all of these techniques will transfer directly. I want to try something. Let's see. Let me do one more. Let me call it number 9 here. How about if we have something like this? 2x plus 1 over 1 plus x squared. Mm, uh-huh. So 2x plus 1 over 1 plus x squared. Just to show you something different that we haven't done. It's similar to something that we have done, but at the same time, it's a little bit different as well. Okay, so if you want to do something like this, first of all, notice that the 1 over 1 plus x squared, we know how to deal with that, right? So that's our tangent. If you think about it this way, if you only look at this, if we had this integral only, that's an arctangent integral. It's the derivative of arctangent. Good. So I could split and get that expression. The question is, do we know how to do this one? And the answer now is yes, we know, because if we let u be equal 1 plus x squared, then du is 2x, which is exactly what's on top. Okay? So we are in business. So we can write this as, so the idea is split two integrals. Okay? The last integral, we know exactly how to do it. That's so really what happens is that I split it I split the fraction into two, into a sum, and then we have the integral of a sum into some of the integrals. Okay? So now, the last one we can do it. That's just inverse tangent of x. So we get that directly. Now, what can we do here? All right, so you can do a substitution just like what we just did, but now let me show you something a little bit quicker. What's special here? Here we have a function, so that it's a fraction, so that when you do the derivative of the bottom, it's exactly what's on top. So this has the form f prime over f, right? Where the bottom is a 1 plus x squared, and the top is derivative. If you think about this, hopefully, the natural log function should come to your mind together with the chain rule. So if you take the derivative of ln of f, what is this derivative? When you take the derivative of this, remember chain rule is f prime over f. So whenever you see this, that you have a fraction and in the denominator, the derivative of the denominator is exactly what's on top. This is just automatically ln of the bottom. So now here I can write ln of absolute value of 1 plus x squared, and that's fine. But as you know, 1 plus x squared is always positive. So if that's already positive, the absolute value is a redundancy, so we don't really need it. Okay? All right. So again, if you don't want to deal with this, what I just told you, then just to solve this little integral, what you will do is a little substitution. Okay? So you let your u equals 1 plus x squared, then du is 2x dx. So this exactly becomes 1 over u du, which gives you ln of u, but then u is 1 plus x squared. And you realize, oh, 1 plus x squared is positive, so there's really no need for the parentheses. And then for the absolute value, and then you can exchange it for parentheses. But if you leave the absolute value, that's okay. It's fine as well. All right.